All right. Hello, everyone, and welcome to this technical community call for October of 2025. I'm your host, Ed Marcus. I lead developer relations for Hedera at Hashgraph. And let's remember that Hashgraph is not just that amazing consensus algorithm powering the Hedera network, but also that entity, that firm driving significant initiatives in engineering and marketing for the Hedera ecosystem. And as usual, we have an action-packed agenda with very interesting topics and great updates for you today. So you're going to be hearing from open source leaders and product leaders in the Hedera ecosystem and also in the software world. So before I bring our presenters, I want to go over some housekeeping items, right? The first one is this call is being streamed to multiple channels. So that includes YouTube, X, LinkedIn. Please amplify, share it with your network so that others can stay informed and learn about Hedera as well. This call is also being recorded, so you can always go back and rewatch it if you missed something, or if you want to study another segment of the call, you can always do that in your own time. And right now, you'll see overlays in the screen, sharing important information, important announcements, so keep a lookout for that. And last but not least, I also want to call out the great efforts of the guys behind the scenes, Luis and Fermin, our community managers, making these calls possible, making all the coordination run very smoothly, and enabling those 4 to 5 live streams that we run and bring to you, the community, every month. All right, so let's kick things off. Let's bring our speakers to the stage, and we'll start with some introductions. So very happy to have Hendrik, Mark, welcome back, and also Ty, welcome back. So we'll do a quick round of intros, and we'll start with Hendrik. Hendrik, if you could tell us what you do and a little bit about yourself, that'd be awesome.
Sure, absolutely. Hey, I'm Hendrik, and yeah, I'm the director of open source at Hashgraph, which means like I'm leading everything that we do as open source strategy, heavily related on the Hiero project where we'll talk on today. I have an open source background. I'm in the Eclipse Foundation actively and in the Linux Foundation. In the Eclipse Foundation, I'm even a member of the board. And trying to bring all those open source expertise and how to run open source in large for enterprises to Hedera, Hashgraph, and so on, with especially the Hiero project, where I'm leading the TSC, which is the Technical Steering Committee, and about my work and what I'm doing there, and maybe what is Hiero, what is Hedera, how does it fit together? Those are the things I would like to talk today.
Amazing. Well, great to have you with us today, Hendrik, and can't wait to get into that topic in more depth. Next, we'll go to Ty or Patches. Patches, welcome back. Please tell us a little bit about yourself and what you do.
Yeah. Thanks for having me. Excited talking about some fun HIPs and open source stuff today. I am Ty, or you might know me as Patches. I've been in the Hedera community around 4 or 5 years, and then I work at Hashgraph as a senior product manager focused on the token service, the consensus service, and helping with the AI strategy for Hedera.
Awesome. Great. And then last but not least, Mark, welcome back. We just had you last month talking about block nodes, block streams. People wanted more. We heard the feedback, and so we have you back. But please tell us a little bit about yourself.
Yeah, happy to be here. Thank you so much, Ed and team. My name is Mark Blackman. I work with Patches and the product team, really focused on the platform, which includes nodes, algorithms, and data streams. And happy to say we'll be continuing the conversation on a massive upgrade to the network output layer. So really excited to come back and dig a little deeper on that topic.
Excellent. All right. So with those introductions, we'll dive right into the content. It's going to be action-packed. And the first topic we'll get into is Hendrik's topic around Hiero, Hedera, open source. So Hendrik, over to you and take it away.
Thank you. Yeah, I already introduced myself, right? So I think we can jump directly to the next topic, which is Hiero and the Hiero project. So Hiero exists now a little bit more than a year. It was announced last year in September, so it's now like 30 months that we have the Hiero project under the Linux Foundation. And in that time, I got asked a lot, like, what is it? How is it related to to Hedera? Wasn't Hedera not already open source? What's now the difference or the benefit of having Hiero? All those kind of questions. I can totally understand that questions for 100%. And so what I would try to do today is talk a little bit about it, try to answer those questions. Independent of that, if you have any additional questions, please put them into the chat. I will try to have a look at it. But let's start maybe with an overview about the Hiero project. So the Hiero project is an open source project that contains the base of the Hedera network. As I already said, it was announced last September, and it is part of the Linux Foundation, and there especially of the Linux Foundation Decentralized Trust, which is like a sub-part of the Linux Foundation taking care about decentralized technologies. There are several other sub-parts of the Linux Foundation, like, for example, the CNCF that takes part about cloud computing, Kubernetes, things like that. There is the JavaScript Foundation taking care about everything around JavaScript. And we, because it makes sense, are part of the decentralized trust. If you have never heard about the Linux Foundation, I will come in a second to what foundations are in general. But the Linux Foundation is like the biggest foundation hosting vendor-neutral open source software of the world. And several of the most critical and biggest open source projects that we have today that driving our world, driving all our critical components, processes, and sectors like finance, medicine, science, whatever, a lot of that is part of the Linux Foundation, as is Hiero today. And what Hiero really is, when you look into it, it's the full source code of Hedera. Because what we did 1 year ago, we donated the full source code of the Hedera network to the Linux Foundation, and we transferred then at the beginning of this year all that source code to the Linux Foundation, which is now named Project Hiero. So what does that mean? I mean, you could ask yourself, like, why are they doing that? I mean, why do they give that away? Isn't that like what really makes a network? And yeah, I would agree in saying this is what really makes a network. But what we're achieving here with moving the source code of the Hedera network to a vendor-neutral place, which the Linux Foundation is, we achieved to have the Hiero project, the first in the world, fully vendor-neutral and open source distributed ledger technology. We will talk about that and the benefits in a second. One benefit that we've already seen is when looking at the adoption of it. So, let me open this one. So here you can see that is coming from tokenterminal.com, who keep track on the development on L1 blockchains. And what you can see here, and I'm really proud of that, is that Hedera is mentioned there as the second project after Ethereum when it's about core developers who are working on the project and contributing to the project. And one of the things why we are here is because we moved it to a vendor neutral point and made it vendor neutral, because what we are seeing is that a lot of people now start to contribute to those projects. A lot, and not only a lot of people, a lot of organizations too. So those are numbers from April. I really need to get new numbers, and that is on my to-do list for next month. But what you can see here, like in the first half year of the Hiero project, we got a lot of different contributions, like over 22,000 contributions coming to the project from over 400 people contributing to it. And we were able already in April to identify over 50 different organizations who contributed to Hiero. And that is a big benefit, because moving the source code of the Hedera network to the open, having it in a vendor neutral manner, allows us and others to not depend on just one single company, because now we have a lot of companies working together to create Hiero, which means Hiero, and I think that's an important message, is not equals to Hedera. I always says Hedera is a product, and this product is using the sources of the open Hiero project to be built and deployed. And since Hiero is now that open, in theory, everybody out there, everybody of you could take the sources of Hiero and create a network. And now you again could say, wait. Does that mean everybody could easily create Hedera too? In theory, coming from a technical perspective, sure, yes. Are we afraid? No, not really, because Hedera is big enough, it's good enough that it don't make sense to have a second public ledger like in Hedera 2. We have already the Hedera network, and it's so good, and with all the partners working on the Hedera network, it makes zero sense to have something in parallel to that. But what makes sense, for example, is to use the technology and create networks like in education space, like in universities, or to create networks in private. Because while the Hedera network, which is based on Hiero, is a totally public network that everybody can use, you can now use the Hiero technology and source code to create private networks, maybe create a network between 3 companies and use that by easily sharing data over smart contracts that only those 3 companies can say, and where only those 3 companies have access to the blockchain, can have their own mirror node to see historical data and all that. And there are always things like that happening. I think the biggest thing is HashSphere, which is a product that does, like, you can think about it as a Hedera network as a service, because HashSphere allows you to easily set up a private network and run it with your partners or within your company. And as I already said, when talking about Hiero, it's not only Hedera or Hashgraph who contribute to it. We already now have a very diverse community contributing to Hiero, and not only contributing to Hiero, but even leading Hiero, because what we have is the technical steering committee of Hiero that are currently 9 people in. You can find them and the information about them on our website, Hiero.org. And those people come from totally different companies. There are 6 different companies where the people on the technical steering committee of Hiero come from, which means you can already say today 6 different companies are leading Hiero, and it's not that the seat that Hedera has more rights or something like that. No. Everybody has the same voting rights, and so on and so on. And that makes what we are creating way more interesting for companies to create private networks, interesting for governance to work up on it, because we're moving it into vendor neutrality, and with vendor neutrality, with more companies coming to it, we move it into something like a standard, right? Because you can have then multiple networks using the Hiero source code, and then all those networks are compatible to each other. You can use the same SDKs, the same clients on a private network, on a Hedera network, or on a university network based on Hiero. And I think that is a huge success, and that is one of the things we are moving forward here. And when talking about vendor neutrality, I think it's always good to have a look at the Linux Foundation Decentralized Trust. Let me go back to, let me close this one, to the Linux Foundation Decentralized Trust, because while it's only a part of the Linux Foundation and only concentrating on the projects regarding distributed ledger technologies and so on, there were already several interesting projects in it, and maybe some you even have heard about, like Bezo, which is one of the biggest Ethereum clients that is part of the Linux Foundation Decentralized Trust and developed within the LFDT, like Hiero is. And more important or more interesting it gets when looking at the companies who contribute to the LFDT projects, and who are part of the LFDT, are official members paying fees and so on. And I just have a list of some companies here, and you see things like MasterCard or Telecom or Huawei or Hitachi or universities or Hedera. I just have highlighted some here, or Oracle or Chainlink. So all those companies are contributing to LFDT and with that contributing to Hiero, right? Here are some others like Walmart, Ethereum, Citibank, and so on and so on. And all that is happening 100% in the open in our, let me open it, GitHub organization, which is the central place where you can find the source code, and where, if you want to, can even contribute to Hiero, and with that to the base of the Hedera public ledger. So if you're a developer, what you can do is, we have a lot, and you see it here on our main page, a lot of community meetings that are all open, are recorded, where everybody can easily join. We have a public calendar. You can even subscribe to that calendar and then just come into our meetings and discuss with us. The TSC meetings, like where all the decisions are made from the technical steering committee, those are open, and you can find the recording afterwards, or if I go to next week, you can easily, by clicking on the Zoom link, join that meeting and discuss with us about Hiero. So feel yourself invited. And one thing we're working on there is to really make even the code base, the projects we have in Hiero, more diverse. And we achieved that on several ways. One interesting thing, just to show you an example, is the Python SDK. Coming from Hedera, there was no real Python SDK to work against the Hedera network. In Hiero, we now have a Hiero Python SDK, and that one got not like migrated from Hedera or recreated now from Hashgraph. That is a project that is coming out from other people of the community, and they currently work on creating a Python SDK, a Python client that is as good as the one for Java, JavaScript, Go, and so on that we have. And the nice thing is that on this one, while it's totally community driven, we already have 58 contributors. Because what we are doing is we work on things like good first issues, trying to integrate people into it, and so on. So I talked a lot about the openness of it and where to find those information and how to maybe participate on it and be part of it. Another thing I would like to talk about, if I have like 2 more minutes, is the HIP process that most of you maybe know, because that is where new features for the Hedera network are defined and have been defined in the past. And in the Hiero in the Hiero, here we go. In the Hiero repository, you will find the Hiero improvement proposals repository. And that is now the source that lies behind the HIPs repo of Hedera. And what I will do is I will open HIP run, because that is the initial HIP, the first HIP that defines the structure of the HIP process. And as you can see, that has been updated this summer because we updated the HIP process with Hiero in mind. And to have a look what this means, there's a nice diagram here in this HIP run. So in the past, after the last call, you had the Hedera review of an HIP, and then it got accepted or not. And as you can see now, from last call, we have two different ways an HIP goes, which is not only the Hedera review, but next to that, the Hiero review. And the Hiero Technical Steering Committee approves HIPs to allow those HIPs to be coded and implemented in the Hiero project. So the Hiero TRC, which is not only Hedera, which is other companies too, review those HIPs and check if they make sense for Hiero in a general manner, that it's not super Hedera specific, that other networks can use it too, and so on. And Hedera can then, in their review, accept it and say, oh yeah, when we deploy a new version to Hedera mainnet, we want to have that HIP once it's implemented, integrated, or if, in the worst case, if they don't accept it, in Hiero, we will need to make sure that this HIP is like activate and deactivate able, so that like maybe a private network want to activate it, but for the Hedera mainnet, it will be deactivated when updating the Hedera network. So this makes the HIP process maybe a little bit more complex because we now have like more boxes here in the diagram. But on the other hand, it makes the HIP process more transparent and more open because we can now really work on generic stuff that are generic for any network, which will help us a lot, again, when talking about becoming standards and things like that. Because doing it here in the open and having it implemented in Hiero and then deployed in multiple networks, that is what we try to achieve here. Next, for sure, which is one of the main goals, to have it deployed on Hedera mainnet, which is the one and only and biggest network that is based on Hiero, for sure, right? Sorry. So that is the HIP process and what has changed with Hiero, and I'm seeing some links are shared here already in the chat. Thanks for doing so. And I think that is my introduction to Hiero and the HIP process. Join our meetings if you have any questions. I'm happy to help you there. And otherwise, I give back to Ed.
Excellent. Thank you so much for that incredible overview, Hendrik. You certainly covered many things, benefits, motivation, where to get involved, where to find more resources, and so on. I do love a point that you made around, it relates to network effects, right? Because when you pose the question of, are we concerned of anyone, or are there concerns of anyone using the Hiero to spin up their Hedera network? It's possible anyone can do that, but it's like the analogy that I like to make in the Web2 world is like Wikipedia is free and you can copy all the content in it.
Exactly.
But your own Wikipedia doesn't mean that it subtracts from the existing networks. If anything, everybody benefits when you open up that technology and those algorithms so that everyone can start their own type of network, whether it's in an academic setting, consortium, industry, and so on. So love that point that you made there.
Yeah. And I like the Wikipedia comparison. I need to remember that. That's a good one. Thank you.
Absolutely. You did mention a lot of the benefits and the motivation behind why Hedera voted to move or contribute all this code to the Linux Foundation Decentralized Trust, or LFDT. Can you give us some insights around the timing? Like, why was it important to do that now? And was there any precedent to a similar move in Web3?
So why to do it now? My personal point of view here is it could, I mean, I think we did it at a perfect point in time, because at the day Hiero was announced was the day where the Linux Foundation Decentralized Trust was announced, right? So like when the Linux Foundation Decentralized Trust started, we were one of the first projects. And we already had this idea about going more into the open, going vendor neutral before, but, and that is something I always said, the most important thing to do that is to be hosted at a trustful base. And the Linux Foundation, like some other large open source foundation, to name, for example, the Eclipse Foundation or the Apache Foundation, those are well-known bases who have good structure, who have like all the legal things you need to do to really move into vendor neutrality. All that is done by those players. And with that, when the Linux Foundation created the decentralized trust like sub part, I was like all in. That is exactly the perfect place, and that is where we need to go and need to be as fast as possible, because we are the first, where I would say is very good. We're exactly the one and only project. If you want to build on something vendor neutral and create your network, you can choose Hiero or Hiero. You know, there is nothing really else you can choose at that case. And so I think with that, it was the perfect moment in time.
Awesome. Thank you so much for those insights, Hendrik. All right, and let's bring Ty on the screen. We'll move on. Hendrik, please stay with us, and then we'll do another round of Q&As. Also, a reminder for the audience, drop your questions in the chat, whatever platform you're watching this on, and then we'll get to those questions after each segment and also at the very end. So now this is a perfect time to transition over to Ty and hear more about HIP 551 or batch transactions. So Ty, take it over.
Yep. Classic muted. But yeah, that was an awesome breakdown. Thank you, Heinrich, just going over how Hiero works. And then he touched on the HIP process. And then this is a HIP. So went through that process, and this brought something called batch transactions to the Hedera mainnet, all networks, testnet, previewnet. And I'm just going to kind of go over, what was this, and why should you care? So for this agenda, first, just kind of like an overview of what are batches. And then we'll go a little bit more. I tried to create this in a agnostic view. So if you're extremely technical, I'll get to that content. And if you're not, it'll still be a high level explanation so you can understand really what's happening and what the change is after HIP 551. So first, we're just going to do an overview. And then second, I'm going to do a technical discussion with a diagram and just kind of go through how, in theory, this works and how it's going through its stages. And then at the end, I'll do some pseudo code examples and get into the nitty gritty and some of the complex, cool things that you can do with this new HIP. So first, what are batch transactions? So a batch transaction on Hedera is a single transaction that contains multiple operations inside of it. It's most condensed kind of definition of it. And so this brings new abilities that didn't exist before, because instead of having to do, say, you want to do 3 different transactions, and if the first one fails, you really don't want to do the second one, because it just now, maybe a payment failed and now you're going to execute some sort of value. And if the payment failed, you really don't want to do that. You had to manage a lot as a developer on the network, or just more, where you had to understand the finality of the receipt of that transaction before you execute the new transaction. People can see the transactions you do on a decentralized ledger, a public ledger like Hedera. So if you did that initial transaction and someone was trying to snipe you or get in front of you before you do the second one, there was a time window where you had to wait for it to propagate to the mirror node so you could read and see that receipt. And then, or if you got it from the consensus node, but someone could maybe inject a transaction that you didn't want them to in between the two. So what batch transactions allow you to do as an engineer, as an app, as a decentralized app, a dApp, it allows you to stack multiple transactions that either all happen sequentially or they don't happen. And so if you have those 3 transactions, but the last transaction fails, none of the transactions actually execute. And none are actually propagated. So it brings a lot of like a hardened workflow, multiple services. It was more hands-on in order to execute these things on network. And after HIP 551, which is in mainnet now, it allows a lot more ease of use for dApps to have atomic programmability of multiple transactions across multiple different services. But there's some information there for engineers and just for people in general to get down a little bit more in the nitty gritty. So the first thing is that the inner transactions are valid transactions, full stop. And so they have their own data. They have their own author and auth, so that they've been signed. They're ready for execution. And they have a fee. And so the fee doesn't change, and the payee of that fee doesn't change. The signatures don't change. It's still a transaction. But when you create this transaction, you can, I'm going to go into what happens, and then there are helper libraries in the SDK, so you don't actually have to do this. But when you use a helper function called batchify, what it's doing is it sets the account ID of the node it's going to send it to 0.0.0, which isn't a node, right? So this inner transaction is 100% valid, but it's not going to actually submit to one of the nodes on the network. It's 0.0.0, and it includes something called a batch key. And that's extremely important, and I'll get to that a little bit later. But so the difference of this transaction is that its node that it's going to submit to the network is just 0.0.0, and it has this extra identifier that says, hey, if this isn't signed by a batch key, this actually isn't valid. So what the batch key allows you to do is it's on the batch transaction is sort of encompasses the inner transactions, and it's the valid signature that will solidify the order of those transactions. And so in a batch transaction, whoever's putting together, so there's a couple ways this could happen. You could be a lone developer and you're like, I want to do 5 things. And so the trust vector is pretty high if you trust yourself. And you go, okay, well, I'm the batch key and I'm going to take these 5 transactions. They're all valid. I batchify them. I put them in a batch. I sign it and I submit to the network. They atomically all execute, or one of them fails and none of them execute. Caveat, the ones that are executing, but then so 1, 2, 3 is successful, but 4 fails, you do pay the fees on the 3 successfuls because that compute is happening, but you have the atomic ability that it doesn't actually happen, right? So it's sort of like how you pay for a failed transaction. You're paying for successful transactions, but they don't happen because they're never posted to the network. So that's a little caveat there. But the batch key, when you sign it, again, it just crunches that down. That's the order they're going to execute. And if you trust yourself, that's great. You have the 5 transactions. But when you're, say, in a DAO, and the DAO has 4 transactions they want to do, and the transactions signed are from 4 different accounts, and you're going to sign and batch all these, you would say either the DAO threshold key is the batch key, or let's just simplify it in this example, it's just one account key. It's a regular ECDSA. And so all of those members would create their transaction. They sign it as they would. And they point to that public key of the account they're going to give it to assign it and put it in the correct order. And there's trust there now. You're trusting that account to put it in the right order, sign it, and send it to the node. And so the batch key is extremely important. And just to explain a little bit on why it exists, if you did not have the batch key, just to assume the most malicious situation, when you do submit that batch to the network, if the node that receives the batch wants to be malicious and moves one of those transactions or injects a transaction into that, if it wasn't crunched down into bytes, there would be an ability for the node before posting to the network to maliciously inject things, change the order. And so this batch key brings, as we continually expand our phases of node network, this allows any node to have no ability to manipulate what's been submitted. And so that trust is just on who owns that batch key, who's signing it to crunch down those transaction bytes and sending it to the node. And after that, the node can never adapt it, or it's invalid and it'll break. And then it brings that, the decentralized trust that we really want to have in DLT. So the batch key is very important. And that's, sort of how it works in practice and why it exists. So batch transactions, again, they bring some more composability to engineers and to developers. And so you have this enhanced security where, again, if I have 3 transactions and I really don't want to do that second transaction if the first one failed because the first one had some monetary value, something happening, you now have that security, integrity in your system where if you make it a batch, that will never happen. And so that simplifies a lot of workflows. That allows you to do kind of cooler things where you can have different services. So you can do a smart contract call, then you can do an HCS call, and then now you can do a token call. And that is atomic. That is all crunched together. So if any of those fail, none of them happen. And that's really powerful. And so it's a simple sort of addition, but it's really powerful for applications to sort of extend their conditional logic outside of an EVM environment, right? This is sort of like a trustless execution of transactions of native services for Hedera. And they're little snippets of verified, deterministically this is going to happen or it's not, all 3 of those transactions. So that's the all or nothing execution. Super powerful, really nice to have it in again, more of a piecemeal, isolated native environment for the native services on Hedera. And it simplifies your workflow as developers. You can now bundle these transactions across services. You can know that they're all going to happen. And then again, you can even coordinate between a bunch of different accounts doing a bunch of different transactions, put it all into the batch, and then the trust person signs it, submits it to the node, and now 7 accounts all do transactions deterministically in this one execution on native services that was never possible before this hit. So there's a lot of really cool stuff. I'm excited to see what developers do. Every time we add a new HIP, developers in the Hedera ecosystem just do some cool, crazy stuff. But excited to see what really starts being developed in the next months and years from this new ability of, again, deterministically executing across a bunch of different accounts. Either happens or doesn't. So that's a lot of talking. I feel like I got a little technical in the non-technical part, and I apologize for that. But maybe this is the better non-technical section in hindsight. So here's a visual, which I think visuals really help, especially in decentralized ledger technology where it's extremely complex. Here we can see Alice has signed and created a transaction, and that's the signed transaction number 1. And Bob has signed and created a transaction, and that's transaction number 2. And they put that into a batch, or they submit it to the batch submitter. And they say, here's my transaction bytes. They're 100% valid. And we want these to go in this order. And they trust whoever is going to squash that. Alice could be the person who's the batch submitter. In this diagram, I just made it a neutral third party. It could also be a service that's created down the road from a third party that creates batch submits. I digress. So 2 transactions, both valid, both signed, and both use in the JavaScript SDK, there's something called batchify. And I'll get to that in the code snippets in the future, but that makes it, again, so that node it's pointing to is 0.0.0, and so that there's a batch key. And so the system, the network knows this is meant for a batch. So if Alice were to send it to the network, it would just fail. And they give it to the batch submitter, and the batch submitter puts it in the right order. And then the batch submitter's account key is the batch key, and they sign it. And then they submit that to the Hedera network. So they sign with the batch key, they submit it to the network. And if transaction 1 fails, nothing happens. If transaction 1 is successful, It's a successful run, and then transaction 2 fails. Nothing happens, right? Those transactions, again, incur fees, but as far as a state change on the mainnet, there is no state change. It is just those transactions do not go through. Transaction 1 doesn't go through. Transaction 2 doesn't. If they both succeed, then both of those transactions are successful in order, in sequence. And so they happen atomically. Both of them go through. And you know that, again, you have that deterministic viability of native services now, that if 1 and 2 are successful, what happens? If anything goes wrong, that end result is not going to happen. So I hope this diagram brings a little bit more contextual visuals to it. And then let's go down into code examples. What does this look like in code? So when you're creating this transaction, it's pretty easy. It's not difficult. Again, this is in the newest JavaScript SDK is the examples I'm using. And you can see, I'm going to mint a token and transfer it. So you could make that atomically. If the mint doesn't work, obviously the transfer is not going to work. So you can batch that. Here you set the token ID, you set the amount of the token, and then this is the simplified version. So you don't have to do the nuance below the scene or behind the scenes. Just .batchify, and you pass through the client that you've initted with your private key and your account ID, and then the public key of the batch key. So it's really how most saying you require a signature works. The public key is the way that you put into the transaction, and then when you sign it with the private key, it'll match. So you freeze that with the client, and then we go to the transfer. And we can see, just go transfer some HBAR for the value of that minted token. You batchify that transaction and you freeze it with the client. So both of those are now ready to be put into a batch transaction. So here, I hope I named those variables the same. I did. Look at that. So here we have the batch transaction, and we're going to create a new one. And we add the inner transaction, which is the frozen transaction of the mint transaction. It's valid, right? And we saw it. And when we did that batchify command, again, it puts that the node and the what's the key signing that it needs to be valid in there. Then we add the transfer transaction, and that's the second transaction. And the order that you're doing these inner transactions in the batch is extremely important. If the first inner transaction you add to the batch is going to be the first one, and that's the path. So don't mess that up. You really want to make sure that that's in the right order. And then after you get those transactions that were made for a batch and you put that into your inner transaction, you freeze it with the client, and then you sign it with the batch key. From there, you execute it. Just submit it to any node, and then you can get the receipt, as you can see. And then you can get the inner transaction IDs as well. So if you want to see the state or the transaction ID on, say, Hashscan, you can do this little for each that we have at the bottom to get all the transaction IDs and the receipt statuses. And then you can know not just if the batch was successful, but if you need, say, the token ID of the successful mint or something like that. You can use that to access that information post either success or failure of the batch transaction. So that's batches. I'm pretty excited about them. I think they're very cool. Again, the creativity of our community is unmatched. I'm biased, but I believe that. And I'm very excited to see what you guys do with this new functionality. And the last thing, I think this is extremely important. Every transaction does need to be valid and signed. And so this is not a skip to the end. I want to do 7 transactions, so I'll put them in a batch and I sign 1. That's not the value add of batch transactions. The value add is I know all of these will execute in this order or not. So you do still, if you put 7 transactions in a batch, you're gonna have to sign 8 times. It's the caveat there. But with that, I'll send it back to you, Ed.
Awesome. That is, you heard it, everybody. That's batches from patches on Hedera. And so thank you for that great overview, Ty. And I believe you got into this because the EVM did have similar functionality where you could have a contract call that has inner transactions, but it's absolutely a game changer to bring that here to the native Hedera services, to have that atomicity in the execution and the path of transactions that folks can specify. So just like you, I'm very excited to see what our developers and the ecosystem end up building with this. All right, so just a reminder here for the audience, if you have questions for Ty on HIP 551 or batch transactions, please drop them in the chat, or leave them in social media. We'll get back to you, and then we'll also be capturing questions for the very end. So I don't see any questions coming through right now, Ty, but again, thank you so much for that incredible overview, and then we'll get back to you at the very end with some additional questions. So with that, I would like to bring Mark to the stage. And Mark, so yes, you were with us last month covering block nodes, block streams, and now I know you have some reminders, but also a deeper dive to cover today. So with that, over to you, Mark.
All right. Thank you very much, Ed. Yeah, as discussed last time, we talked about 3 HIPs and how they overarch and really interact with each other to update the network output of the network. So we'll go into one of those HIPs and the details here. But firstly, just wanted to talk about a HIP 1299, which enables node operators on the Hedera network to change their node account ID. So Ed, if you could skip to the next slide. So how are node account IDs used? So this is a required field in transactions. And basically it is used to facilitate the node fee payment. So the payee pays the node for the service. And in that, you have to specify which account to make that payment to. And additionally, it is used for penalties. If a node does due diligence failures, the penalty will come from this account. So very critical, very foundational to the network and for a required field for transactions. So you need to get it correct. Next slide, please. So looking at this, you could see we now enable nodes to change their account IDs. This is using the dynamic address book feature, which was released December last year. But now nodes can say, hey, my node account ID is now XXABC. And through a transaction on the network that gets processed by all the nodes and eventually ends up in the mirror node, and the address book query from the mirror node is updated with that new information. So very straightforward HIP here, enabling node operators to change this account ID. However, in the next slide, you'll see the impacts of this. Now, SDKs that are configured for auto refresh will automatically get that update from the mirror node and change their internal address book to the updated value, submit the network with the updated node account ID, and everything is good. You get back a success. However, older SDKs or SDKs that are configured for hard-coded nodes will not get that update. And it's up to the developer to update that address book within the SDK. So in that case, the old account ID, node account ID, will still be in the transaction and it'll fail with an invalid node account message. So we really want to over communicate this fact and this risk for those that are using hard-coded address books or older SDKs. Next slide, please. So there was a blog written about this in September 25th. I highly encourage you to look at that blog. In that blog, you'll see the compatibility chart. If you're using these versions of the SDK or above, the auto refresh function is on by default and you are good. But then again, I just want to say if you're using an older SDK or hard-coded address book, you'll have to manage these changes. We're going to work with the council members to try to get early notification on specific Node Account ID changes, but it is a decentralized network and they're able to do this on their own. So no guarantees there, and really want to strongly give you a call to action on this. So yes, let's get on to the block streams overview. Next slide, please. So Hedera is a modular network. We have really the Hashgraph consensus algorithm and transaction processing is really what a lot of people focus on. But we also have a data output layer to the network. And this today includes many different data streams coming from the nodes, going to public cloud buckets across many different providers and many different geographic locations. And then Mir nodes, which is a relational database that organizes this information and has a set of RESTful APIs that users, dApps, developers use to see really the outputs and the result of their transactions that they submitted directly to the node. So on the next slide, you'll see we are upgrading this network output layer. This is a forklift upgrade. This is a major update to the network and one we do not take lightly. So why are we doing this? A, we're increasing the speed of delivery of the data, so the end-to-end latency will be reduced. This also reduced costs of processing and storing the data. So not only for the sustainability of the network itself, but also Mir node operators and downstream data service providers. The cost of processing the data also goes down. We're gonna make more data, primarily state data, now available to the public, increase the stability or the scalability of the network by offloading services from the consensus node to other nodes, add state proofs and other features, and then also support the decentralization of the storage of the network. So it's really these values and these benefits that this change brings to the community and to the network. This is why we're taking on this work now. So the next slide, you could see the last call we had, we went over the 3 HIPs that comprise this upgrade. And I have a very obnoxious acronym for this, TSSBSBN, but basically this stands for Threshold Signature Scheme, the TSS, that is HIP 1200. This provides an aggregated threshold signature so that the output data of the network can be signed with a network signature as opposed to each node signing their own output and then the verifier having to collect all that data to verify. So the TSS is a huge upgrade to the cryptography we use for the output data. Block streams is a data format. This is what we're going to go over today, but this is really a format that optimizes everything into a single stream and reduces duplication and other benefits, which we'll get into. And then the block node 1081. This is what's going to add new levels of data services and data streaming capabilities, filtering, et cetera. So really more on the processing of the data. Next slide, Ed, please. So as mentioned, we're going to focus on block streams. Next call, we'll do a deep dive on block node. And then finally in December, we'll do the TSS hints topic. But for now, let's get into block streams. Next slide, please. So block streams HIP 1056, as mentioned, this is a new output data format. This replaces the existing data streams, which include event streams, which many of us are familiar with. record streams, which many of us are familiar with, event streams, which is more on the consensus algorithm related aspect of the network, state files, which is a new capability we're bringing to the public, and finally, signature and sidecar information, sidecar files being the smart contract execution. We are combining these, consolidating these into a data single stream to allow for self-contained, independently verifiable blocks of data. The consolidation brings a lot of deduplication and cost optimization, and really, very importantly, from a user experience standpoint, less end-to-end latency. So let's get into the details. Firstly, though, let me describe how the network output works today so we could fully understand and appreciate the changes that are being made. Today, each node sends out multiple streams. As mentioned, we have the record files, which are consumed by mirror nodes, which really give a audit record and history of the transactions processed on the network. Then we have a stream of signature files. So each record file has signatures, a signature file from the node sending that record file. And today, mirror nodes have to collect many versions of the same record file sent by many different nodes and their associated signature files to do verification. We have the event stream. This is really, again, on the hashgraph consensus algorithm. These are the messages sent by nodes during that consensus process. Today, that is streamed out and really used for disaster recovery and other really network-centric tasks. But we're opening that information up with block streams. And then I mentioned sidecars, which are the smart contract output. And then every 15 minutes today, each node will do a snapshot of its state data and load that entire snapshot to a cloud archive. So again, we're bringing that information through block streams. So let's get into the block stream side of the solution here. So from this chart, you can see, wow, quite a lot has changed. Firstly, each node is sending one stream, one data stream. So we no longer have those separate data streams, but all of the information from those separate streams are consolidated into an optimized data format. Additionally, as data is processed, it is sent. And we have what we call block items. So for example, if a transaction goes through the network and is processed, a block item with the input and a block item with the outputs of that transaction are sent in real time. And then downstream services and a block node will reconstruct those block items into a block. And another thing that's very important is this block is associated with a round of consensus. So the hashgraph algorithm processes transactions in rounds. And prior to block streams, you could have one single round divided into multiple blocks, which was suboptimal for a few different reasons. But now with block streams, the round boundaries are part of the block. So a block can have one round, which will be the case upon launch. But as the network continues to scale, we could put multiple rounds in one block. And so basically, these block items are put into a block, which is a Merkle tree-based data structure. So this means you could have verifiable proofs directly within the block itself because the data is organized into a Merkle tree structure. And then this block of data is signed by the entire network through TSS. And again, this allows one proof to really attest to the fact that a majority of the nodes had signed off on this block, that this is indeed the record of the network. So this really, as I mentioned, provides a lot of improvements. First of all, we get rid of the multiple data streams. The fact that we're sending block items as they are processed reduces end-to-end delays. We're including state data now, which enables the block node and other downstream services, or even your homegrown services, to maintain state of the data, either with all the data or just a piece of data you care about. And then because we're able to consolidate all this data into one stream, we have deduped the data. So there's cost savings and just efficiencies by getting rid of that deduplication. So next slide, please. So as blocks are being processed, just as with record files, we're creating an immutable blockchain format. So as I mentioned at the beginning, Hedera is a modular platform or modular network. And as we know, consensus runs on the hash graph consensus, which creates a DAG data structure, or what we call the hash graph data structure. But the output of the network is done through a blockchain. So these blocks of data are hashed in a running hash. So the hash of block A is in block B, and the hash of block B is in block C, so that these are cryptographically chained or linked together, which means that it becomes tamper resistant and a mutable record of that data. The start of the block stream and the end of the record stream will also have this cryptographic link. So the block stream will continue once we update this new data format. Next slide, please. So I mentioned as information is processed, we will immediately be sending that information in via block items. And so here is a list of the block item types. Each type really represents a component of consensus. So we have the block header, which represents the start of a block. The round header, again, the consensus round is signified in this output now. The events, which are the the consensus messages sent across nodes. And then for each transaction, we'll repeat the following block items: the event transaction, the result of that transaction, the output of the transaction, any state changes related to that transaction, and then if it's a smart contract, the trace data. So for each event, you'll see the headers repeated. For each transaction, you'll see that list of block items that I just mentioned will be repeated. And then for every round, you'll see the round header is repeated. So in the next slide, I kind of break it out just to make it a little easier to understand. So in this case, you could see from top down, left to right, block items are sent. So we'll first get a block header, and then round header, and you could go through the list of block items, but really this represents one block with one round of consensus comprising of two events with one transaction in each event. So there are non-transactional state changes. These are related to consensus. For example, the consensus weight state change would be an example of state changes that occur but are not triggered by transactions. Now, this is conceptually laid out to illustrate how block items come together into a block. But in the next slide, we'll get a better representation of the actual data format of a block. So as I mentioned at the beginning, the block will be a Merkle tree structure. So you'll have this block root and then the tree, Merkle tree below the root. And what a Merkle tree is at a high level is each node of the tree is hashed. And then as you go up to the tree, you hash together those leaves for the next node up. So for example, you could see node 2 is a hash of node 3 and node 4. And then node 3 is a hash of node 5 to node 6. So while this is computationally expensive, it allows a few powerful things. One is that block root becomes kind of the watermark of all the data within the tree. And so you could quickly compare different data sets and validate that no tampering has been done to the data within the tree. Otherwise, the hash root would be different. So this also brings, because of that, immutability to the data in the Merkle tree. So our Merkle structure here really has the different things required. But at the bottom, you could see where these different trees from the block items are constructed together. So from that bottom row, we have the previous block hash, which we described is what's really powering the blockchain of this output data. We have a root of all the block hashes. This is kind of getting into the weeds, but used for providing efficient and scalable proofs. We have the state root hash. So this is all of the state data for that round and that root node of that tree of state data. We have the headers. So these are, think of the event data. We have all of the transactional inputs, the transactional outputs, and then a list of all the state changes that have occurred within that round and the root of all those block items comprising those state changes. And then at the end there, we have the smart contract trace data. So all the block items within a round are organized into these separate subtrees that all roll up into one block root. That block root is part of the TSS signature. So from that block proof, we could prove that a majority of the network agrees that this is the block of information that was processed within the round or rounds of consensus that comprise that block. So very, very powerful change in primitive for our network. Oh, I could change the slides here, I guess. So what are some of the benefits of this? As I mentioned, the decrease in end-to-end latency. With record files, as transactions were processed, they were really just stored locally on the node for 2 seconds and put into a file. And then after 2 seconds, that file was sent again to cloud storage and consumed eventually by the mirror node. There's really two problems with this. A, as mentioned, the benefits of the decrease or the latency that this introduces, but then also blocks, while they're processed using consensus time, which is the time clock of the consensus algorithm, we're publishing them using wall clock time and delayed by 2 seconds. So the timing of the network is kind of lost when we're sending the data out. So one thing that is nice, in addition to the decreased end-to-end latency, is we're now matching consensus time both in the consensus processing and then in the data output. So again, on the left side, we see what's happening with the existing record file format. Data just stays there on the consensus node for up to just under 2 seconds and then sent. But on the right-hand side, we could see with block streams, as transactions are being processed, as state changes occur, the consensus node is immediately sending out granular block items of that information. And this allows Mir nodes and other subscribers to these streams to begin processing that data even before the round of consensus has completed, even before the block proof is produced. You could start processing that data, which again will bring down the end-to-end latency and really increase the user experience by that decreased latency. Additionally, with the block streams and us sending block items as they're produced, is it enables better filtering. One of the major problems or areas of opportunity we have with the existing data output format is you need to consume all of the network data from a Mir node standpoint to be able to get out individual data of interest. But now with block streams, you could subscribe to either a type, a block item type. So I only want to see transactions, inputs or outputs. I only want to maintain state with the network. So just give me state related block items. Or you could filter by specific entity. So I only want to know about my accounts, and I'm going to subscribe to that filtered stream so that I'm only sent the data I care about. And this could be any specific entity, an NFT, smart contracts, accounts, etc. So another very impactful benefit, I would say, to these block streams. And then lastly, and I'm just very, very excited about this aspect of it. Each block is independently verifiable. And just to give an example of that, we went over the Merkle based structure of the blocks. So for example, if you could see at the bottom there, transaction 1, I really need cryptographic assurance that that has been successfully processed to the by the network. So there's an API that will be available, and I would say, hey, give me the Merkle path of my transaction within this block. And at that point, you'll get that full all the data that rolls up to the root hash. So you could see all the data that isn't grayed out here. You get the hash of that transaction node with the hash of the transaction X or the next leaf, and that rolls up into node 13, and then you validate node 13. And then the hash of node 14, which rolls up to node 7. And likewise, you go all the way up that path, recomputing the hash, verifying that it matches with the Merkle path that was given. And then eventually you calculate all the way back to the root of the tree. And then you verify that that root is what is in the block proof. And so through that, you could be assured that a majority of the network has signed off that your transaction is in that block and has been successfully processed. So these are what we call block contents proofs. There's also state proofs, which is another level of proofs, which we'll go over when we deep dive into the block node. But these are proofs that can be done by just having a copy of that block. You could take, if a meaningful transaction, say you bought a very expensive NFT and you want to have an insurance policy on that, you could download this block and put it on a thumb drive, and then off-chain forever be able to verify cryptographically that was processed by a majority of the network. So very, very powerful, powerful feature here. Additionally, with this, we're adding state data, as I mentioned. So state data is the data on the node that has all of the balances you could think of. So, hey, this NFT is assigned to this account, or this account has this many H bars. That is the state of the network, and that is stored in a Merkle tree database on the consensus node. We're now adding all that information to the block stream. And what's very, very cool about this is we're not only mentioning the changes that have occurred to that data. So if one account has one H bar added, we're also including the end result of that piece of state. So you could see the final value would be 5.65 H bar, because before the state change, they had 4.65. So this means that if you're consuming this state data for an account or a topic that you're interested in, you don't have to maintain the history of all the deltas or the state changes up to that point. You could see within that one block the resulting value, which if you take the previous slide and have a block contents proof for that state data, you basically get a state proof directly embedded in that block, which is, again, a very, very cool thing, particularly as blockchains become legitimized and legal record for many, many things within life. So let's get into some use cases. So this is obviously in the US Post-Clarity Act, but a family buys a home using an on-chain escrow service. And this smart contract holds the funds and then is also monitoring the township or the register for when that deed is transferred. And so it is subscribed to the block stream, waiting to see when the deed is transferred online. Once it gets that information from the block stream, the funds are given to the seller, and the deed is then transferred to that family. And for record-keeping services purposes, the family downloads the exact block in which the deed was transferred by the city. And that block, put it on a thumb drive, put it in a secure area, but that block of data could be used off-chain and even offline for verification purposes, proving that that deed was transferred and processed successfully by a majority of the nodes on the Hedera network. So what this results in is faster audits. You're not dealing with paperwork and having to go to the city to have them get the official document. So this is really enabled by that verifiability, that Merkle tree aspect to the block, And it allows you to download the BLK file, and from that, be able to forever verify all the information within the block, which is comprised of one or more rounds of Hedera consensus. So let's go to another use case. This is a logistics firm that has 10,000 truck sensors on the network. And they subscribe to a filtered data stream that includes only transactions from those sensors. And so they get these GPS update alerts as they come. They immediately send those, verify those from the block proof, and then store those in a local database. And then the clients are able to look at that in a real-time dashboard for route optimization. This not only reduces latency, better user experience, but again, the data is verifiable. So let's say there was some refrigeration issue, some food was spoiled on these trucks. They could go back as the transportation provider and cryptographically verify what the temperature of the truck was or was not at that point. So the ability to subscribe to a filtered stream and get that data in real time as it's being produced, and then verify that with the block proof really enables this use case. And lastly, let's look at a DeFi use case. We have a DEX that is using block streams and the block contents proofs to verify cryptographically that transactions have occurred, and they could do that again. They could start processing the data before the block proof comes, and then once the block proof comes, they could verify it, and this brings much better end-to-end latency, which allows not only better user experience, but no slippage, and really could scale at Hedera scale for high volume DeFi. So this low latency, low cost verification is really what enables this specific use case example. And really, again, is going to be a powerful tool for DeFi along with other use cases. So that is it for me. Happy to take questions, though.
Mark, I gotta say that when we first spoke about TSS, Blockstream, block nodes, from that first instance until now, I've sat through like 7 or 8 different presentations, but this one is by far my favorite deep dive on Blockstream. And I think you did a fantastic job making it really easy to understand that organization of the block items, that relationship with the events, and also how all these transactions, the items, and those events roll up to the root hash of the block via Merkle tree. So I think that was an amazing overview and great job.
Thank you. Thank you very much. That's nice.
All right. So I do believe we have some questions. We'll start with you, Mark, and we can also bring all the speakers to the stage. So everyone listening, please, this is the moment to engage with these awesome speakers and ask questions. So we'll start with a question about Blockstream and block nodes. I'm trying to find it here on my screen.
Sure.
And the question starts with a comment. So with Blockstreams now providing a unified and verifiable data source for all Hedera network activity, how does Hedera address potential trust concerns? For instance, ensuring that mirror nodes or third-party indexers can independently verify the integrity of the data without relying on solely a consensus node signature.
Yeah, so we're going to get into the guts of this question when we do a deep dive on TSS, but this is quite of an improvement. So previously, as I think you're alluding to in your question, you had to download multiple record files from multiple blocks and their associated signatures. Truly, to verify it, you had to download from more than half of the network to ensure a majority of the nodes are sending indeed the exact same record file. And given that complexity and that cost, it was primarily mirror nodes who were providing that validation. And so you had to trust the mirror node in that circumstance, unless you wanted to go to the bucket and download those directly. With block streams and TSS, this enables a network-wide signature that needs to be verified. So each block, regardless of what node it comes from, can be verified from this TSS signature. And so that allows really anybody on the network to validate that block. And as I mentioned, if you download the block file, you could do this verification offline, off-chain, on a PC. So the verification upgrade that TSS along with block streams brings, really anybody could verify the data rather than having to rely solely on a mirror node to aggregate all of those signatures and records. So yeah, great question and a great upgrade with what we're doing here.
Excellent. Thank you, Mark. All right, we'll give another few seconds to see if anything comes in for our folks, for Hendrik on open source and for Ty as well on batch transactions. Well, we wait for questions to come in. I mean, we're very close to the top of the hour, so I want to maybe give also the speakers to give us any closing thoughts, any last ideas. I do have a couple of reminders to share. So the first one is I want to invite you to participate in the Hello Future Ascension Hackathon. So that's the information and the QR code that you see here on the screen. Great opportunity to get involved, try these technologies, build with batch transactions, get more familiar with Hiero, and so on. The second reminder is we do have an upcoming price increase for the consensus message submit transaction in the Hedera consensus service. So please look out for the communications that have been sent out 3 months ago and a couple of weeks ago. We'll send some more, but remember that is upcoming. So please plan accordingly your price, your usage cost, your cost forecasts, and your usage of HCS, as that is going to be active on the network starting in January 2026. And then the third reminder that I want to share is that just a few minutes ago, it was announced where HederaCon 2026 will be and when. So if you want to come and join this vibrant community in person, that's going to be on May 4th in Miami with Consensus. So there you have it, folks. HederaCon has just dropped for 2026, and looking forward to that exciting opportunity to network with the Hedera community in person. All right, so we're almost at the top of the hour, but anyway, closing thoughts from our speakers, Mark, Patches, Hendrik. Please, if you have anything, this is the time to share.
Yeah, I'll just say really delighted by the interest from the community, and want to just mention that the upgrades that I'm talking about in the past few meetups and the next few will be coming next year. So don't want people to panic or think this is coming this month. We're giving very early notice to developers and mirror node operators, and we will do this in a very measured, safe way. So no call to action right now on the topics I'm discussing.
Yeah, just appreciate the community call. I think it's an insane amount of great information here. Yeah, I'm glad that HIP 551 is out. I'm excited to see what people do with it, and I just learned a ton more about block streams. Thanks, Mark.
Yeah, agree on that. Block streams are great, and if you're watching that maybe even later in the week call and have some questions, right? So I think all of our inboxes are open. You can find us on Discord or on GitHub if you want to contribute, or on LinkedIn. And if you have any questions regarding Hiero, regarding how to contribute, or maybe how to set up a small Hiero-based network just to play with it, just ping me or the other people. I think we're more happy than help here.
Absolutely. I want to echo what each one of you guys have said. And certainly what Hendrik said, join the Hedera Discord. So if you go to hedera.com/Discord, that's a fantastic place to start engaging with the community, asking questions even about all these topics that you heard about today and beyond. And we're so thankful that you were able to join us today. Thankful with the speakers that you were able to join us today to share all this knowledge and all this information. So with that, we'll call it a meeting, and stay tuned for the one coming up in November. So we'll see you guys in the next call. Thank you all.
See you.
Cheers.